Example 6.6. Consider a square-shaped loop, wire of circulation in the xy plane, such that the circulation, right-hand rule, is in the positive z-axis direction. The side lengths of the square are 2a. What is the magnetic field on the z-axis, e.g., at a distance z from the xy plane? Solution: on the z-axis, the non-z-axis directed contributions from the loop cancel and we are left with a purely axial component, invoking symmetry. The magnitude of the magnetic field due to a conducting segment of length 2a, centered vis-a-vis nearest point, was determined previously to be. See the next equation. Here we have the superposition of four such components, and then their projections in the z direction. See the equation shown. And recall that r equals a squared plus z squared to the 1/2. Thus see the next equation.
Example 6.7. Consider the classic Helmholtz coil configuration consisting of two parallel coaxial loops where we seek to maximize the region between them with uniform field. What is the relation between the loop radii, a, and the loop axial separation of d to maximize this region? Solution: recall the magnitude of the axial magnetic field due to a circular loop, coaxial, where loop is centered at the origin and in the xy plane, and the current circulation, right-hand rule, is in the positive z-axis direction, satisfies. See the equation shown. Where z is the distance from the center of the loop on the coaxial z-axis. We have two such loops, one placed like above, and another, parallel, with center at z equals d, so the total axial magnetic field is. See the next equation.
Also recall the classic Taylor expansion. See the equation shown. And to have this be constant in a large region we need f prime of a equals 0 and f double prime of a equals 0. Thus, we start with the first derivative. See the next equation. This is 0 when z equals d divided by 2. Let's now consider the second derivative when z equals d divided by 2. See the equation shown. If we substitute a equals d, the square bracket expression becomes 0. Thus, to achieve the largest region of uniform field, separate the coils by a distance equal to their radii magnitude.
Example 6.8. Let's crush a thin metal tube by passing a current through it. Let's assume crush failure occurs when the magnetic field strength reaches the fraction with numerator 9Wb and denominator m squared equals 9t, and that the tube radius is 2 centimeters. What is the magnitude of the force per unit area? What is the direction of the force? Solution: at what current will we obtain a magnetic field strength of B equals 9T, where B equals mu sub 0H? Recall: see the next equation. So crush failure when see the equation shown. Since we have dF equals IdL times B, see the next equation.
And see the equation shown. Thus, the force per unit area is see the next equation. We recover direction of the force, inward, by Lenz's rule, where stability requires reduction in flux area coupling, thus crushing. Example
6.9. Consider a coaxial transmission line with inner conductor having radius a and out having radius b. There is a permeability of mu sub 1 f of OR times A is less than R is less than D and therefore B is less than R is less than D, with mu sub 0. For R is less than A, denote the permeability by mu. What is the inductance per unit length? Solution: we have. See the equation shown. See the next equation. See the equation shown.
Thus, the energy can be obtained in 3 parts. See the next equation. See the equation shown. See the next equation.
Thus, see the equation shown. And the inductance per unit length is thus. See the next equation.
Example 6.10. Consider a line current running parallel to a superconducting plane. Superconducting in the sense that a mirror problem is established vis-a-vis magnetic field lines. Not how this mirrors a similar problem with electric field of a line charge parallel to a regular conducting mirror. Thus, B sub n at the surface is 0, as is the tangential H sub x at the surface. What is the surface current density? Solution: we have an effective parallel wire transmission line problem. The vector potential due to a wire of current is. See the equation shown. Let's orient the coordinates and wires such that the superconducting plane is the YZ plane. The wires are a distance plus or minus d in the x direction. The wire at x equals positive d runs parallel to the y-axis with current I. The wire at x equals negative d has current negative I. We have for finite wires. See the next equation. And, as L goes to infinity, see the equation shown.
Using B of R equals gradient cross A of R, and H of R equals 1 over mu B of R, see the next equation. And see the equation shown. Thus, see the next equation.
As expected, and see the equation shown. Since J sub S equals N times H on all surfaces, we have the surface current to be. See the next equation.
Example 6.11. Consider the parallel plate transmission line running in the z direction with plate thickness h and separation d, in the x direction, and current plus or minus I, in the z direction, with width in the y direction w. What is the internal inductance per unit length? Solution using I equals the contour integral from 2 of h dot dl and considering the edge effect negligible, we want to determine. Let's make our line integral run in a rectangle enclosing a length w in the z direction of the upper plate, and a variable extent, x, into the plate, with its thickness d. Thus, for h0 is less than x is less than d, see the equation shown. Thus, see the next equation. Since potential energy U sub h equals the integral from v to of mu over 2h squared of dv and considering internal inductance per unit length. See the equation shown. Twice this is the total potential energy due to both conductors, and since U sub h equals Li squared divided by 2 we have, see the next equation.
Example 6.12. Consider a wire of radius c with a uniform current density. Inside the wire is a parallel cylindrical void with radius b. That doesn't include the origin. The enclosing wire is directed in the z direction, with xy cross-section, and relative to that coordinate system the void region is centered at x equals a, y equals 0. We have b is less than a is less than c and b is less than c minus a. For this to be consistent, what is h of x for 0 is less than x is less than infinity? Solution: use superposition to find h field. Without the void and with the uniform current density J, we have see the equation shown. Using a concentric circle with radius r is greater than c. See the next equation. And we have for h field outside the wire. See the equation shown. Once inside the conductor I becomes a function of radius. I of r equals r over c squared times I, so this is changed to see the next equation.
Or, if considering only the positive x-axis, this becomes h sub phi of x equals ix over 2 pi c squared. The void represents a superposition of a negative current, uniform density negative J, upon the original conductor, with analysis much like before. Considering only the positive x-axis, we have r equals x minus a for the void which is displaced from the origin. Now to combine, or superpose, for x is greater than or equal to c, see the equation shown. For a plus b is less than or equal to x is less than or equal to c, see the next equation. F of or times a minus b is less than or equal to x is less than or equal to a plus b, see the equation shown.
For 0 is less than or equal to x is less than or equal to a minus b. See the next equation. Note: magnetostatics versus electrostatics in cylindrical coordinates. Electrostatics has only associated Legendre polynomials while magnetostatics requires both association. And ordinary Legendre polynomials can reach one from the other by analytic continuation, point one of many signs of finding the larger theory by analytic continuation.